Okay, so example a plus b squared. So obviously it equals to a plus b times a plus b, which equals to a squared plus 2ab and plus b squared. Because that's what our teacher taught us when we were doing the binomial distribution, or like in other words, like the perfect square binomials. But today let's just think it another way. So after expansion, how many ways can I choose 2a's from this expression, which consists of 2a's and 2b's? So that's either 2c2 or 2c0, which all equals to one way. But what about 1a and 1b? So that should be 2c1, which is two ways. So because when we are multiplying this equation out over here, we're basically just choosing random letters from this equation, which consists of 2a's and 2b's. So when I'm writing a squared down, so that's basically a times a, which is considered 2a right here. And because I only have one way to choose 2a, so the coefficient in front of a should be 1. So I just write 1 over here. So because I have two ways to choose 1a and 1b, so the coefficient before the term ab should be 2. And because also like I just only have one way to choose 2b's from this equation, so the coefficient in front of the term b squared should be 1 as well. Okay, so this might confuse a lot of you guys, but let's just look at another example. So this is really similar, but I just changed the square to cube. So what is the value in general of a plus b cubed? So that's indeed equals to a plus b times a plus b times a plus b. But let's just also think this in another way. While we are expanding this binomial, how can I choose 3a's from this expression, which consists of 3a's and 3b's? So that's indeed 3c3 or 3c0, which is one way. And how many ways can I choose 2a's and 1b from this expression? That's either 3c2 or 3c1, which is three ways. And how many ways can I select 1a and 2b's from this expression? That is 3c1 or 3c2, which is three ways. And how many ways can I choose 0a and 3b's from this expression? That is also 3c0 and 3c3, which is one way. So according to what I just said before, the number of ways can determine the coefficient in front of each term. So according to the thing that we already have right here, we can just basically determine the rule for this cube. So that should be, because I don't have one way to select 3a's, so the coefficient in front of a cube should just be 1, which is the thing that I'm not going to write it down. So, and 2a's and 1b. So 2a's right here, I mean 2a's are being multiplied together, so that should be a squared. So this is a squared and b. Because there are three ways, so the coefficient in front of this term should be 3. And similar to this, 2b is 2b's are being multiplied together, which is b squared, and then times a. And then because there are also three ways right here, so I'm just going to write 3 in front of this term. And finally, because there's only one way for me to choose 3b's in this equation, so the coefficient before the coefficient before the term b cubed should just be 1. So this is basically we already finished the expansion without even calculating and multiplying out every term and collect all of its like terms. So that's just really, really convenient, right? So here is the conclusion. The coefficient of each term in binomial is the number of possible ways that we can choose a specific variable. Therefore, we can express the coefficients as a combination of selecting a number of variables, such as 2a's in example b, from the expression. Okay, so the next thing that we are going to be talking about is the Pascal triangle. So here is some background information. So Pascal triangle is basically a triangular array of the binomial coefficient that arises in probability theory, combinations, and algebra. Okay. So here is the formula for us to calculate NCK according to the Pascal triangle. So the number of the nth row and kth column of the triangle can be expressed as NCK, with the topmost row to be considered as 0. What is also really interesting is that every number in the triangle can be written as the sum of the other two numbers right above it. This can be denoted by the mathematical formula below. NCK equals to n minus 1 c n minus k plus n minus 1 ck. So that is basically the mathematical expression of what I have just described above. So the relationship with binomial distribution. Not surprisingly, Pascal triangle can also determine the coefficient in binomial distribution. Here are some Pascal triangles with all numbers are being expressed in a combination formula. So what I meant by that is this picture is actually the exactly same thing as the picture that I have just shown you guys, but all of the numbers in this triangle are just being written in the combination form, so they're basically the same value. So 0C0 is 1, and any number true 0 is just 1, so these are all 1, and 2C1 is 2, and we can just try out the rest, but we don't have that much time, so let's just move on. So let's consider the topmost row in the triangle still be 0 and from left to right. The first term of each row be 0. In general, the coefficient of each term after the distribution should be the number of the row which the exponent of the binomial corresponds to. The distribution of a binomial can be denoted as the formula below. Okay, I know that this formula may seem really complicated and scary, but in order to understand this formula well, let's just try some really simple examples in order to demonstrate that this formula actually works out. Okay, so let's just try a really, really simple and typical one. X plus y squared. So we all know that this should be x squared plus 2xy plus y squared. But let's just try it out and plug in number and to just basically use the formula. So then this should be 2c0, which is 1, times x squared plus 2c1 times x to the power of 1 times y, and plus 2c2, which is also 1, times x to the power of 0, which is just basically 1, then just times y squared. And surprisingly, after simplification, we can easily tell that this equation is also x squared plus 2xy plus y squared. Okay, so that's just a really, really simple demonstration of how this equation or formula works. And this can for sure to be applied on all of the binomial distribution, no matter how high the power of this binomial is. And yeah, just if you guys are interested in the expansion of this formula, just like try out in your spare time, and I promise that this will be really, really interesting.